Hello. Today we will be analyzing the motion of a falling object. We will do this by first taking the video recording of a falling object and tracking its motion with the tracker program. We will then compare that observed motion to the motion predicted by a computational model that's created using VIDLE with Python. We will later find that the two models actually fit each other pretty well. I'll start by exploring the physics concepts that govern the motion of a falling object. As in the case of constant velocity motion, the motion of a falling object also is governed by Newton's second law, where the final velocity equals the initial velocity plus the net force over the mass times the change in time. But unlike constant velocity, the net forces in this case aren't equal to zero. The two net forces that we have acting on this object that give this non-zero net force is the force of gravity and the force of drag, which we will use in our model. The force of gravity is modeled by the mass of the object times the gravitational constant for Earth. In our case, g is 9.8. The force of drag, so it's proportional to the square of the velocity, but it's only a constant. Now, the direction of gravity is in the motion of the falling object, and the direction of drag is against the motion of the falling object. That's why there's negative here and there's positive here. The motion I studied was that of a falling, balled up paper towel. The camera I used to filmed at 240 frames per second, so we can get a very accurate reading of the paper towel ball's position as it's moving down. As you can see, I've got the ball moving in the negative y direction, and I've used the diameter of it, which is 4.5 centimeters, as a calibration stick for the distance that it's moved. As you can see from this graph, its movement in the x direction did vary, but that was just because of the small size of the ball, and being able to track it in a straight line was pretty difficult. But its movement in the y direction does look like it's moving at an increasing velocity downwards, as is expected by the model that I'll show you now. Here's the code for the model, the computational model for the motion. As you can see, I've got the mass set to 22 grams, which I knew. The initial position and velocity is 0 because it started at the 0 point in my coordinate system, and it's not moving at all when I first drop it. Notice this would have been different if I would have thrown the object down, because then the initial velocity wouldn't have been 0, and it would have completely changed the predicted motion that we would have gotten from the model. In the actual loop part of our code where it keeps predicting the motion, we've got the net force equals the force of the weight, which is the force of gravity, times the force of drag. The force of weight is in the same direction as the motion of the ball, but because in my system it was moving in the negative y, this is also negative. And as you can see, I've got the mass of the ball times the gravitational constant, and this is just a unit vector so that it moves in the y direction. The force of drag is opposite to the motion, so it's negative b, which it's a constant I predicted based on the final position of the observed motion, times the velocity squared, so it's proportional to the square of the velocity. Since the velocity is moving negatively, this will actually end up being positive total, so we'll be moving an upward force. So the net force I've got right here, and then finally Newton's second law, where the final velocity equals the initial velocity plus the net force over the mass times the change in time. Now let's see how this runs. As you can see, you've got the force of gravity bringing it down, and you've got the force of drag pushing it up against the direction of the motion. And also you can see a graph that looks like constantly increasing velocity in the negative y direction. I also ran this program without including the force of the drag, so I set the drag constant equal to 0, b equal to 0. And I've gotten this motion with that other motion where drag is 0 and put them onto a chart with the observed motion, which is right here. So here's the predicted motion, the green line, without the drag. And this makes sense because it over predicts where the ball is going to land because it doesn't include an upward force acting on the object. The blue line is the predicted motion with the drag, which fits the observed motion much better. So the only place where the observed motion differs from the predicted model with the force of gravity and the force of drag is right here in the middle, and it's only very slightly, where the observed motion is a little bit higher than the predicted motion. This slight, almost negligible difference could be due to me not tracking the object properly, just some human error in the tracking, or it could also be due to me not picking the perfect b value, the perfect drag constant for the motion. But it still predicts it very accurately, and we can conclude that the motion of a falling object can be accurately predicted using Newton's second law, with the forces of gravity and the forces of drag being the forces acting on the object to create a net force that isn't equal to 0.